Do you have any questions about stuff? I don't know where my whole class is. I haven't been seeing some people. Actually, I know where Isaac is. He'll be here in minutes. Any questions on things that are due? Okay, so last night I went into your grade books and I put zeros for everything that's not done. So your grades, some of you took a big tank because now instead of not having anything there, you got zeros for these assignments. So if you need to do something about it, then you need to do something about it. But I'm not going to hold your hand. You're in college. I give you assignments, you do the work. Julia, thank you for submitting them. You're good, right? I took care of that. But those were only two. There's a bunch of you who haven't been doing your other things like notes and chapter outlines. So any questions on what is coming due? We will have the test soon. Let me just talk about the geography lab. I don't want to grade it online, and I'm not going to print out all your stuff. So I kind of made sure that you got most of them right. I think you did most of it okay. I took out points if you had maybe a thing here or there that was missing or a little bit messy or something like that. If I could find something easy to write on, I would do that. But anyway, that's just geography. Usually I give a geography quiz. I'm not going to give a quiz because that's annoying online. Anything else? Ryan, anything?
No, I think I'm good.
Okay. All right, then let us go on to what are we doing? What was the last thing we did?
I remember last class we kind of reviewed lambda and lambda max with the wavelengths of
Okay, so
sun and Earth.
now you need to go back and look at that lecture again. I would suggest that you do that just to make sure that you know that, because it's been a couple of weeks since we've done anything together. It's been 12 days and you're going to forget everything, and the test is coming due soon. Now, did we talk about selective absorptivity? And when I say selective absorptivity, I know that we did talk about it. So I want you to define what that means. What do you have on that? Now, I believe that we did this a while back. It might even been in another unit where we talked about it and then we kind of referenced it in this class or in our later section. Lena, what do you remember about selective absorptivity?
I'm trying to remember. I don't really remember talking about that.
Are you guys finding it anywhere in your notes? Aaron, do you remember what that is?
End of what? What? C? E? Certain? M? O?
Isaac.
Certain molecules. What? A? B? Absorb?
Yes, that is correct.
Certain colors, yeah.
Am I sharing my screen?
No.
Good job.
There we go. So when I go to this, if I do this, let me go to the images, hold on. Certain gases absorb certain elements. And we did this type of diagram. You remember this? Although this is, remember I showed you this one, I said, oh, this is not good because it's upside down. And I think we used something like this. No, this is upside down. Where is it? This one. So we have the wavelength down here on this axis, and it is a logarithmic scale, see 100, 10, 1, 0.1, etc. And we're talking about what gases absorb different types of radiation. So it's not just color, right, Aaron? It's you're defining the type of radiation. Color is going to be a specific band within the visible spectrum. Okay, so in this case, we talked about oxygen and ozone and carbon dioxide, water vapor being, these are the primary gases for infrared. These are the ones for ultraviolet. We said that little blip was like 2%. Remember doing this? We've done that. So you need to make sure you know that. Okay, so this is what's going on at the local level. But what's going on at sort of global, we need to do something along these lines. And so what I'm going to say is we are going to create a global annual energy budget where we get radiation coming in from the sun. It comes into the atmosphere and then it goes to the ground. So really what I'm looking at in this energy budget is that some of the radiation is going to come in to the atmosphere. Now, when the atmosphere may include clouds, they certainly include gases of the atmosphere. And what did we say happens to this radiation as it comes in to the atmosphere?
Do you remember?
What's going to happen to the radiation as it comes into the atmosphere?
They get absorbed.
Okay, it could be absorbed. What else?
Reflected.
Some of it is going to be reflected.
It can get reflected. And what's the last thing?
It can pass through.
Okay, that's a good word. I'll use that word, pass through, transmitted, right? Then when it hits the ground, the stuff that passes through hits the ground, what happens to it?
It gets absorbed into the earth.
It can be absorbed or,
Re-radiated.
well, no, not yet. I'm talking about the stuff that's coming in. What else can happen to it?
Can also be reflected.
You said it exactly right. It can also be reflected. Now, the amount that's reflected is called the albedo. And typically, high albedos, when we talk about the surface, are going to be two things. What are they going to be? What will, at the surface of the earth, what will cause a high albedo, high reflectivity?
One of them is snow.
Snow definitely has an albedo, but what I'm trying to say is what are the two generalizations of the surface that reflects a lot?
Would it be a white color then?
Okay, so I'll even just go light color. Right, the lighter the color, the closer to white it is, the more that's reflected. So snow and ice, in that sense, it's going to reflect a lot. What else? Besides the color. What do you think, Ryan?
I'm not sure.
Here, imagine this is the surface of the earth. Imagine that I've got some grasses, and over here I've got a bunch of trees. What do you think is going to be easier to reflect light?
Which one? Is it?
I would think the grass.
Okay, so the reason for that, it's all about the texture. The smoother something is, the more reflective it will be. Right? So the texture, grass is less textural than forest. Plains are more flat than mountains. So you're giving it the light a much better chance of doing some reflection. So light color, and it would be smooth texture, is what gives it a high albedo. Now, what about this? What about water? What do you think water has? Do you think it reflects a lot or absorbs?
Aaron says absorbs.
Okay. Water generally, keep this in mind, has a low albedo. Because most of it gets absorbed. In fact, what's happening is it doesn't get absorbed right away. It actually passes through water, because that's why light can be underneath water, because you can see underwater, right? It gets darker the deeper you go. In fact, I was told once that the difference between a lake and a pond is that a lake, the light doesn't hit the bottom, or there's some diminishment, whereas a pond, you can have life all the way across, at least plant life or something. So water will ultimately absorb it. It does not reflect it. This is not true if the light's coming in at an extremely low angle, because when light goes into water, it doesn't go straight, it turns. There's an angle there, angle of refraction. If it comes in less than the angle of refraction, then it's going to reflect. So when it's on the horizon, water has a high albedo, very high albedo. And sometimes when you're seeing waves, you'll see glimmers of bright light from the waves, because you're getting the angle just right that it reflects light. But generally, water has a low albedo, so that's something to keep in mind. And since 70% of the Earth's surface is covered with water, most of the light that hits the Earth is going to be absorbed by the Earth. There's actually, when you look at what is the Earth's albedo, by the way? What's the Earth's albedo in total? Isaac, you remember that?
I don't think I remember.
Anybody? What's the Earth's albedo as a whole? What number?
Aaron says 30.
The Earth's albedo is 30. So 30% of this radiation is reflected. Of this number, only 6% is coming, no, I'm sorry, 4% is coming from the ground. So out of 100% coming in, 4% is reflected by the Earth. What does most of the Earth's reflection? Clouds. Clouds are going to be doing the majority of the Earth's reflection. Then we're going to talk about this too. This is coming up. Radiation also scatters. It goes all directions. So when radiation goes to the sky, it's going in all different directions. Some of it goes back to space. So this is called back scattering. And that's 6. So 20 plus 6 plus 4 is 30. And that's what the Earth's albedo is, the percentage reflected. Okay. Now that leaves how much for other things? It leaves 70%. About half is absorbed. About half is absorbed. And that leaves, about 20% absorbed in the atmosphere. And what's going to be doing a lot of that absorption? On the incoming radiation, what's doing a lot of the absorption?
The water.
In the atmosphere.
Oh, in the atmosphere.
Is it going to be the ozone?
Ozone, which is absorbing 98% of what? What kind of radiation? What kind of radiation does ozone absorb?
Ultraviolet, UV.
Okay, and do you remember we said about 7% of the Earth's sunlight is ultraviolet? So it's absorbing about 7% of the 20 is coming from ultraviolet radiation. Don't forget, up in the thermosphere, gases are absorbing some radiation. There's a few other gases that absorb some of it, not very much. Remember, we said that we have an atmospheric what doesn't absorb visible light. What's the word I'm missing in the blank? What's that called? An atmospheric what? You should have written this down, so go take a look at your notes.
Aaron says window.
Aaron, you're talkative today. An atmospheric window. An atmospheric window doesn't absorb visible light. Remember, the window is the part of the spectrum that is not absorbed. So that's all coming in. Now, the Earth gets warm and it starts to radiate out. But this time it's what we call OLR. Sam, you should know this. What does OLR stand for?
Outgoing long wave radiation.
So the Earth is giving off infrared or terrestrial, or what we call outgoing long wave radiation. And most of it is absorbed by the atmosphere. So that absorption is the greenhouse gases. Okay? That absorption is greenhouse gases. Some of it goes out, not much. Most of it, like, I don't know, 90, like, let's say more than 90% is absorbed going out. So clearly not an atmospheric window. But then what does the atmosphere do? The atmosphere getting warmer, because remember, it's radiation coming in. It radiates, some of it goes out, some of it goes back. What do you call the part of the atmospheric radiation that comes back to the Earth? What do you call the part of the radiation that the atmosphere radiates back to the Earth?
That'd be the greenhouse effect.
That's the greenhouse effect, right? Greenhouse gases are absorbing it. They radiate some of it back to the Earth. Some of it goes up and is lost to space. Now, the thing that's important is because this, so pay attention here, because this is a global, meaning we're averaging it over the entire world, not at any one place, and annual, meaning it's over the course of a year, what we're saying is that what comes in has to be equal to what goes out. What if more came in than went out?
The plant would warm.
The planet on a whole, on a yearly average, would get warmer. If more went out than came in, the Earth would get colder. Now we're going to see that this is not always exactly equal. Okay, it's not actually equal, but we'll show you that. And they're saying that some of the water is absorbing heat. The oceans are big enough that they can absorb excess heat. They will eventually radiate because think about this. Now I want you to think something that you don't think about with global warming. When you have an object, if more comes in than goes out, what will the Earth do? Zach, you just said it.
It would get warmer.
And what would happen if the Earth gets warmer?
Um, Isn't like CO2 wouldn't absorb as much?
Well, I mean, those things are possible, Zach, so I'm not going to say you're wrong there. What is this law right here?
That is the Stefan Boltzmann's law.
And can you give it to me in English, Lena?
Yes. Hold on. I have the rate of energy flow via radiation through some area is directly proportional to the absolute temperature to the fourth power.
No one can say that you don't take fantastic notes,
Thank you.
right? So in other words, if the Earth got warmer, then the Earth would radiate at a greater rate. So in other words, there was an imbalance, more coming in than going out. The Earth would get warmer and radiate more energy because what is it always trying to do? The Earth is always trying so that the income and the outgo are the same. That is what we call an equilibrium. By the way, you may see this if you really want to know about global warming. If you are talking to people about global warming and they can use this term or what we call TCS, that term, this stands for equilibrium climate sensitivity, meaning increase the concentration of CO2. At some point, the Earth becomes an equilibrium at some temperature, some average temperature. That is the ECS. TCS is something called transient climate sensitivity. It's based on how much time, how long it takes to do that. But this is really what we're trying to figure out. What is this value? How much warmer would a doubling of the CO2 result in of the Earth? That's what we're trying to figure out. Hard to do, it's not simple. And there's estimates and there's uncertainty in this, but this is what they're really talking about. Because if more came in than went out, the Earth would get warmer, so that more goes out. It's just the way it goes. Now, looking at this diagram, would you agree that this diagram is fairly complex?
Yeah.
Right? So it's kind of messy. I'm going to show you, I'm going to go online and find some better diagrams that will help you. I think you have this in your book too. But this one I was creating with you, so we were talking through it. Is there any question that you have about anything?
Okay.
Now, the last thing that I want to point out to you guys is this. When I do all the numbers with radiation, what I find is that on a global annual basis, more in than out on the surface of the Earth, and the atmosphere has more out than in. When I look at the numbers, listen to what I'm going to say. Pay attention really closely. When I look at the numbers for radiation on a global and annual basis, I've got more radiation coming into the Earth than goes out of the Earth. But I have more going out of the atmosphere than going into the atmosphere. How is that possible? Let's talk. I want you to talk out loud. I'm not going to go to breakout rooms, not with 8 people. You can all talk.
Well, the atmosphere with emitting more out than in, would that be because of the ozone with how it reflects so much UV?
No, remember, because don't say reflect. When you
Absorbed.
talk- When you talk about reflect, right? Reflection is like I always make this as an analogy. When you're playing catch with somebody, you throw that person the ball, they throw that ball to you. If you went to your sibling and took a baseball and started bouncing it off your brother's head, are you playing catch with your brother? No, you're just bouncing baseballs off his head. Might be fun for you, but it's not fun for him. Okay, so in other words, catch, the earth absorbs, that's playing catch. It absorbs and gives off. Reflection never came in. It's sort of like the 30% is sort of like income tax, right? You might say, oh, I'm making $15 an hour, but after taxes, you're only making $11 an hour. You don't even see that other $4, right? It's not even given to you. So you start thinking, well, what I net versus what I gross. This is clearly on the long-term yearly average, more comes in than out for the earth, but more goes out than in the atmosphere. How is that possible? Well, if that were the case, what would the earth be getting every year?
The earth would get warmer and the atmosphere would be cooler.
Wouldn't the earth be getting warmer and the atmosphere be getting colder year after year? That's not the way it works. So how do you explain this energy budget?
Aaron says it's differential heating.
No, because, okay, so the differential heating, which is true, remember we said at what, 43 degrees latitude, there's an in versus out. North of that, you have more out than in. South of that, equator word, we have more in than out. But that's not the global average, right? So this is taking into account that differences from point to point. So that's not correct either. How about it, Julia? Can you figure that out?
I don't know, like, if this is even close, but would it have to do with, like, the day versus the night? Like, because you would be, like, absorbing more during the day?
Well, okay, because we're taking it into consideration over the year, that's not going to influence this. But like the day and night, right? At night, you have more out than in, so it gets colder. If you have more than in coming out, it gets warmer. So why isn't the earth getting warmer? Because this is, right, I'm telling you that this is true. This statement is true. This statement is true. But the earth is not getting warmer and the atmosphere is not getting colder.
Well, wouldn't it still be equal? Because even if you have, like, if you have less on this side and more on this side, it's still, like, equal. If that makes sense. I don't know how to word it.
Okay, you guys, Julia's on the right track. Can you help expound on that? What do you think, Ryan?
That's a hard question.
Julia, try to.
So
Go ahead, Ryan.
so we're seeing the like Earth itself is gaining energy, but the atmosphere is losing it
So,
for the year annually.
yes. And Julia says, well, if that happens, Julia, how would you explain what you said? Because you're on the right track.
Because the atmosphere has more that it's putting out than the Earth. Wait, hold on. If you think of it like, okay, if it's like they're both giving 50-50, that's like 100%. But if like the atmosphere is giving 75 and the Earth's giving 25, that's still 100%. So it's equal.
And you originally did this with your hands.
Yeah. Like, I like have it in my head, but I can't put it into words. Because if they were both the atmosphere and the Earth.
So you're saying that when I put them together, they all balance out.
Yeah.
That's what you're thinking, isn't it? So how does that happen?
Because
Does it have to do something with the? Sorry.
No, go ahead, Ryan.
Does it have to do something with the fact that the Earth radiates into the atmosphere?
I'm telling you that, let me rephrase this, because I said pay attention very closely. Look at inside this box. And I said, when I look at the numbers for radiation, these two things are true. This is for radiation, this is for radiation. But what does it say here? Okay, let's break it down into first week material, first week of class. What is radiation?
Transfer of energy.
Correct. It's a transfer of energy. Is that the only transfer of energy?
No.
What are the other two methods?
Conduction and convection.
So in other words, when I look at this budget, this is an energy budget. This is not a radiation budget, it's an energy budget. When whoops, somehow I just, whoa, where did you go? There. Somehow I changed, I made you guys all really huge in my window. Man, tell me that I get to get rid of Zoom one day. Damn it. What is going on here? Oh, here. There. Okay, now you're all in my window again. This is an energy budget, not just a radiation budget. Radiation is only one way. So the other two ways are conduction and convection. So how does conduction work? Isaac, remember beginning of the semester. What is
Conduction is when the energy is absorbed.
not absorbed? What's the word that you should use? Like, do you have your notes from the very first week? Go take a look at the definition of conduction. Anybody know Tim? I don't know where Tim's been lately. Kind of miss him. Are we missing somebody else? I know we have a couple people who don't show up as often. Is Hannah in our class or is that the other class?
I think a different one.
What did you find it, Isaac?
No.
Who found
I
it? What do you go ahead, Lena?
Yeah, for conduction, I have the transfer of heat from warm to cold by contact.
Okay. Do you agree that the ground would be warmer and the Earth's atmosphere would be colder? So there's going to be some transfer of energy from the ground to the atmosphere through contact. That's conduction. But what kind of heat is it? There's a name for this heat through conduction.
Sensible heat.
It is called sensible heat. Sensible heat. So conduction. And that accounts for some of the difference. On average, the ground is warmer than the atmosphere. And therefore, there is an energy flow from the ground to the atmosphere. The other one must be what? What's the third method?
Convection.
Convection.
Okay, what's the definition of convection?
It is. Oh, go ahead, Julia.
Sorry. Transfer of heat within a fluid by a fluid.
By the fluid motions, right? But is the ground a fluid? I mean, you could say the oceans are, but I'm transferring it from the Earth to the atmosphere. The atmosphere is moving. If it's in the atmosphere, it's in the atmosphere. But how do I do that? How do I transfer the heat using convection? Sam, this one should be important to you, from the ground to the atmosphere. And the term is convection.
Does it have anything to do with like mixing?
Mixing is in the atmosphere, but that means once it's in the atmosphere, you could mix it up.
Mm-hmm.
And certainly we have circulations that move the excess heat. That's convective. But how does it go from the ground to the atmosphere? The ground is not part of the atmosphere. What do you think, Zach?
Could you just repeat it one more time? Sorry, I'm just still trying to think about it.
Well, convection is the transfer of heat within a fluid by the motions of the fluid. Why am I using convection if I'm going from the surface to the atmosphere?
Would it be like evaporation and then?
So I am taking excess heat because the ground's warm, right?
Oh yeah, and then
What does the excess heat do?
It will turn the water into the gas.
Right? So if I evaporate water, and that water may be in oceans, lakes, rivers, it could be in the ground soil, right? The earth can evaporate water from the ground. Once it evaporates, where is it now?
It's in the atmosphere.
It's now in the atmosphere. And what kind of heat is it?
Would that be the latent heat found in the water?
Latent heat. So I'm taking heat hidden. It's in the vapor, but is that really part of the temperature yet? No, what has to happen is it needs to go up where the air expands, cools, and eventually hits the LCL where it condenses. So when water vapor condenses, what do you say?
Latent heat is released.
Latent heat is released. Right? So you're taking heat from here and you're releasing it to the atmosphere. But what if the cloud just evaporates in the night? Do you understand the evaporation will take the heat back? That's not good. What does this thunderstorm or cloud have to do? it needs to rain. Because if it rains, there is heat released to the atmosphere, then what's causing the rain to fall? That's a really easy question. What causes the rain to fall?
Gravity.
Gravity. Duh, right? So in other words, I've got water on the earth going to vapor, forms as rain, falls back. What is that called?
That's just the water cycle.
Give me a more scientific name for it, Zach.
Um,
What's the more scientific name for the water cycle?
What? H. Y. T.
This is what-
Aaron says hydrologic cycle.
Good. I heard your dad spelling it out. So hydrologic cycle. That's the water cycle. So the hydrologic cycle transfers heat from the ground to the atmosphere. This is necessary, as is conduction, to balance the entire budget. Radiation alone does not balance the budget. Once again, I'm going to go back to something in terms of global warming, in terms of climate change. We are changing the radiation aspect of it. Do you know how difficult it is to figure out, well, how does that change the amount of evaporation and precipitation that falls? Because that plays a big role in balancing the budget. And we don't really know a lot about this in a global long-term future. It's hard. By the way, I'm going to go way off the deep end here and say one more thing that I think is interesting. You remember we talked about global warming. Where do we care that it's getting warmer? What's getting warmer and where does it matter?
Is it at the poles that
Well,
melts?
it could do that, but so Ryan, yes.
Oh, by sea lines?
What I'm really basically saying is that I'm looking at the surface temperature getting warmer. But if the surface temperature gets warmer and the upper atmosphere doesn't get warmer, then what is the lapse rate of the environment doing? Sam?
Wouldn't it be increasing?
If I have a greater lapse rate, what do we know about that? The air is more what?
Gonna rain more?
Well, it's more what?
Saturated.
stable.
Humid?
No. If the greater the lapse rate,
Unstable.
the more unstable the atmosphere. If there's more instability on a global average, wouldn't you expect that to result in more clouds, more thunderstorms? If the global average instability is greater, I would expect more thunderstorms. If I have more thunderstorms, do you see that the hydrologic cycle is more aggressive, transferring energy from the ground up? So clouds, what they're basically doing, clouds, and this is where it's going to get really messy, but I don't care. Clouds are in effect transferring heat from here higher up. And transferring heat up, which is convection to a meteorologist, makes the atmosphere stable. So what is the purpose of a thunderstorm? The purpose of a thunderstorm is to make the atmosphere less unstable. And in doing so, it creates rain. Do you see how complicated the atmosphere is? This isn't something simple. One little thing doesn't just change one other thing. It changes everything. And we, as global modelers, don't necessarily have this down really well, which is why there's a lot of uncertainty with global warming. because it changes a lot of things. Anyway, this is a messy diagram. Okay, so what I'm going to do is I'm going to go over here to this, and I'm going to go and I'm going to type in the trend birth energy budget. And when I go to images, I will find all sorts of pictures like this. I don't know what any of these are. This is good enough. So does this look cleaner? Let's go through the numbers. Do you have this in the book? Something similar to this in the book?
I haven't seen that.
Well, either way, you can look this up. And again, I don't care what site, because the numbers are all slightly off a little bit from each other, but whatever. Notice the incoming radiation is about 342. 342 what? (342 watts per meter squared), right? Notice what happens is 77 is reflected by clouds, aerosols, and atmospheric gases. 30 out of 342 is reflected by the surface. 30 plus 77 equals 107. Do you agree? Get out a calculator. Take 107, divide it by 342.
%31.
Okay, so that's around, is it 31 exactly what you get?
It's like 31.28.
Hold on. I'm trying to see, here's one. Okay, look at this. See how the numbers are all different depending on which site you go to? Now they have 341 coming in, and what's being reflected is 102. So what's 102 divided by 341?
That's 29%, 0.91, so like 30%.
So do you guess that in there's about 30%? That's the Earth's albedo. (161) is absorbed by the surface. So what's 161 divided by 341?
That's like 47.2%.
So that's about half. That's what I want you to know. Not exactly half, but about half. And that leaves 78 out of 341 being absorbed by the atmosphere. Got it? Then what comes out of the Earth is 396. That's your OLR. And out of that 396, 374 is what? Is absorbed. So 374 divided by 396, what's that equal to?
That's 94.4%.
I'm sorry, say what?
That's 94.4%.
So do you see that almost 95% is absorbed already? And this always is interesting to me. Well, how much more gets absorbed by CO2? At what point is all of it absorbed? Now, that leaves 22 out of 3, so watch this, guys. Can you follow this? Because I want you to understand these graphs. 22 plus 374 should equal 396. And what does this 22 do? It goes straight out. That's the atmospheric window. That 22 out of 396, 5.6%, just goes straight up.
Our numbers are different.
Okay. Now it's interesting. They have 374 is absorbed, right? What's it absorbed by? It's absorbed by greenhouse gases. The picture makes it look like it's absorbed by what?
Cloud.
Yes, but I mean, clouds do absorb. We said that, but it's, primarily absorbed by greenhouse gases. Okay, then what does the atmosphere do? Well, it's going to go 333 out of the 374 plus 78 that's absorbed, right? Look, what's going into the atmosphere? This number plus this number, and then 333 comes down. 187 goes up from the atmosphere, and then for some reason 30 gets coming from clouds going up. That's not that big of a deal, but eventually you're left with 239 going out, plus 102. 239 and 102 is 341, and what's coming in? 341. There's a balance. Hold on. Let me go back for a second just to show you other pages. No. Look at these numbers. They're different.
We can't see them.
Oh, you mean they're too small?
Yeah.
Oh. I was just like, am I sharing my screen? They're just a little bit different. So am I going to have you memorize the numbers? No, that's silly because they're all slightly different. I do want to show you one thing though.
Why are they so different though between like the different sources?
That's a really good question. What do you think the answer is? Here, let me show you this one. Unfortunately, I don't know why it's cut off there. Notice they're now 341.3. And according to this, what that means is when you look at the incoming and outgoing, you have a net absorbed of 0.9, which means the water is absorbing that excess every year, which makes the water do what? If you're absorbing the excess, what's the water doing?
Cooling?
If it's absorbing the excess, the water is getting warmer. But what happens
I
when
heard it. I heard the question differently.
That's okay. What happens when you heat the water? What do you do when you heat water? Just like you heat air.
Expands.
It expands. You agree it can't dig holes. So what does the water do? Sea levels rise. So you understand we talked about sea level rise being primarily a result of thermal expansion of the water based on this number. Water has a huge heat capacity. There's a whole lot more water than the air in terms of mass. So the waters are slowly warming. So why are the numbers different? Because you know what? We don't know precisely what the answer is. In fact, if I were to do something like this, What is the Earth's albedo? Here's the NASA's Earth Observatory. Sunlight is the primary driver of the Earth's climate and weather, averaged over the entire planet, roughly 340 watts per square meter, right? About that, give or take a couple. And then it goes on for a while. Do you agree that by changing, if the Earth were completely covered in ice, its albedo would be 0.84? That's really high, right? On the other hand, if it was covered by a complete green forest, the albedo would be 0.14. Changes in ice cover, cloudiness, airborne pollution, land cover have all subtle effects on global albedo. Using satellite measurements accumulated since the late 1970s, science estimate the average is about 30%, 0.3. But if you really want to look at the albedo, you see the way it changes year to year. Now, have you ever once in your life thought that the Earth's albedo changes year to year? Well, if it changes, do you understand that changes everything? It might be declining sea ice, increasing dust and soot. There's just a lot of stuff going on here. There's a cool thing here called Earth light. Now, what is it? Earth light? No, what is it? Earth light moon. Earth light is the diffuse reflection of sunlight reflected from the Earth's surface and clouds. So here's a picture of the moon. Do you understand the bright side of the moon is coming from the sun? Can I see the dark side of the moon? Aaron, can you see the dark side of the moon?
Kind of.
Right? Why can I see the dark side of the moon? Because the Earth is reflecting light off of the moon. Do you know what the moon's albedo is? Moon reflects about 7%. There's a couple of things that I want to experience in my life that I never will. One of the things I wish I could do is to take a major league fastball and to hit it just right and to know that it's going to be a home run, right? It hits the sweet spot and you're like, oh, that's gone. And you know, you just drop your bat and you look at it and you trot around the bases. I played softball all my life. And in softball, to get a home run most of the time, you have to run fast because there's no fences. You could hit it really far and they could be out there and throw you out anyway. So I want to know that feeling of hitting a major league fastball. That would be awesome. The other thing that I want to do is I want to be on the moon during a full Earth. Can you imagine what that looks like? The Earth's albedo is 30. It's 4 times more than the moon. It's a lot bigger. Isn't it? So imagine what it's like when you're standing outside on a clear night with the full moon and how bright things are. Imagine standing on the moon. Well, it's always a clear night. On a night when the sun is a full Earth. And how amazing that spectacle would be to see the Earth as a full Earth. I think that'd be awesome. So anyway, they can measure this to determine what the Earth's albedo is because the moon is not changing its composition. It doesn't have an atmosphere to worry about. It's just rock. And why is the Earth so much bigger? Primary reason is clouds. Okay, so given that, let's take a look at this. Let's look at a satellite. What do I can't find it. I'm looking at it. Let's look at this. Full disk.
Cool.
Those clouds are white because they're reflecting a lot of radiation. But if I did this, I think this is even more cool. And I can put it into motion. And do you see the circle of illumination coming out of here? In fact, let's do it. Let's do this. So we can see it over a course of many days. Pretty amazing, isn't it?
Mm-hmm.
And again, I can look at it full color. Blues, greens, browns. What clouds are going to be white? The polar regions, a lot of snow and ice, very white. There's your reflection. By the way, remember we said RGB? This is what, if I looked only at blue light, this is what the Earth looks like. If I look at only red light reflecting, this is what it looks like. Which looks better to you? Let me zoom in now. Which looks better to you? Using blue or using red? So remember we talked about finding aliens. So now I'm looking through goggles that let me see only red light or only blue light. Which makes this picture look better to you?
Red light.
Why? Do you agree that there's better contrast? Why is that? Why does red light allow me to see things better than blue light? What do you think? What color is the sky?
Blue.
Why do we see blue light from the sky? What's the light doing? Julie, I can see in your house windows, I can see the reflection of the blue sky. Although, oh, it's pretty nice out there. A little couple of cues going. You got some nice weather out there, Sam?
Yeah, this morning actually heard my first thunder of the year.
Yeah.
It's actually a CG strike that woke me up.
That's the best.
It didn't even look like it would produce any lightning on radar. It didn't even I was happy with it.
Okay.
We need the rain up here.
Here's the sun. We're going to talk about this today. Blue light comes in. Oops. Sorry. Blue light's coming in and it hits molecules and it scatters. So a person on the Earth is going to see light that's scattering all over. So the sky is blue through scattering. And we're going to deal with this in more detail. But when I'm looking at red light doesn't scatter very much. So if I look at red light, I don't get the sky is in the way. See, because if I see blue sky from the ground up, if I were floating in space looking at the sky, I would see blue light also. So I'm mixing in a bunch of blue light, and that's why it doesn't look as contrasting. Now, it would be nice if we had green. We don't have green. We have what's known as veggie. Veggie we can use to approximate what green looks like. But watch what happens. Look how dark the oceans are. And where there's vegetation, it shows up pretty intense. So when I combine red, green, and blue, and I look at that together, then I get color images that look like this. And let's face it, it's beautiful, isn't it? So let's zoom into the desert Southwest. Isn't that amazing? And look at down here. in the Gulf of California, you can see sediment from this river. What is this river? What is this river down here? You did the geography lab. It goes from here. Well, here, let me do this. The river goes here. What is that river? What is that river?
The Colorado.
That's the Colorado River. What two famous things are in the Colorado River? Well, three things if you count Jimmy Hoffa's body.
Grand Canyon.
Grand Canyon. Do you guys know who Jimmy Hoffa is? Colorado, the Grand Canyon. What else? It's one of the seven wonders of the modern world. Go do web search. Seven wonders of the modern world.
Aaron says Hoover Dam.
Hoover Dam. Hoover Dam is in there. So the Colorado River drains into the Gulf of California here. And you can actually see sediment in the water. Because remember we said sunlight goes through the water? So you can see the bottom of it where all the fresh sand and sediment is in here.
I remember seeing a lot of sediment going into the Gulf after Harvey.
Yeah, well, you can see it right here. It's so bright, the sunlight is so pure in the water, you can actually see the debris and dirt in the water on the southern tip. Because remember, this is the Delta region coming in the mouth of the Mississippi. Let's take a look at the Great Lakes. Look at how beautiful that is. Huh? And if I go back before, oh, actually, let me do this. Isn't that beautiful? Let's go over here up to the north. Look at the waters there. Why are the waters so white?
Fog.
Do they still have ice?
They're still frozen. Our lakes are water. These are all frozen lakes. So these all have all this ice is a very high albedo. Main place. Oh, here's beautiful. Isn't that gorgeous? I mean, come on, these are cool satellite images.
Mhm.
You want to, let's do this. Let's go west. Oh wait, well, how do I do this? I go to Hawaii. Anybody else want to go to Hawaii?
Right here.
Which a little pixelated. By the way, you see which way are the winds? And we're going to find this out soon. What direction are the winds in Hawaii? Anybody know? Well, the winds are from the northeast. They're called the northeast trade winds. Which means when I put a big mountain here in Hawaii, the air is flowing up into the mountain. This becomes the windward side. where there's clouds. And then this becomes the leeward side. When I go to Maui, it's one of the rainiest areas on the earth. Oahu, same thing. And yet one of the driest areas is on the leeward side. That's kind of cool, isn't it?
Mhm.
Can't do that. Well, let's see. Can you see them?
Mhm.
Let's do this. Rainiest spot on Earth. China, one of the areas in Hawaii, Cameroon, Guinea, New Zealand, Colombia, India. So in the United States, let's take a look at where Hawaii is. It doesn't say. Let's. Anybody know where the driest spot on Earth is?
No.
Algeria, Namibia, Chile. It gets 0.2 inches of rain a year on average. Most of the time it doesn't rain. Evidently there is a place over here where there's weddings that people have because it never rains there. Can you imagine getting married on one of the driest places in the earth and having it rain on the one day you finally get married? That would be bad sign. Peru, Egypt, Chile. I think we'd have to go to the driest spot in US. Where do you think is going to be number one?
Death Valley.
I think it might be Death Valley. Furnace Creek, the Mojave Desert in California. Years with no rain, fewest rainy days, driest place of the century. That's kind of fun. I just want to see one more thing just for hell of it. Hawaii. Huh. Of course, the article is in 1926, when the New York Times still told the truth. That was just something I wanted to say because it's funny. Driest towns in Hawaii. Oh, here. Maui. The best sunshine is on the west and south Maui because the winds are the northeast. It's the leeward side. Kanapali. I've been there. It's beautiful. Lahaina. I love it. Good shrimp. Oahu. Koalina. I like this. That's where the Disney place is. So isn't that funny that Hawaii can be so wet and so dry all at the same time, just based on the winds. So anyway, that's what we're looking at. Now, there's last thing I want to show you on this diagram, based on these numbers. And again, like Lena, you said, they're different all the time. So 31.3, I don't know why they changed. And if you ever wanted to know, you would think it would be easy to figure out, but it's not because it's variable. But again, looking at all these numbers, the back radiation is the greenhouse effect, clouds, what's emitted by the atmosphere, et cetera. But look over here, we have these numbers. 7% is by thermals. Heating the ground heats the air because the ground is warm. You know what it's like on a sunny day when you walk on barefoot, right? In a parking lot, super hot, you're heating the air. And when you see the air, when you see the mirages, what you're seeing is light's bending because it's such a density difference. But you're transferring heat from the ground to the atmosphere. And that's known as thermals. So this number here, just so that you have this in your notes, is conduction. Then evapotranspiration. Transpiration, by the way. Anybody know what transpiration is? Transpiration is from plants. So the leaves put water from their leaves to the atmosphere. In fact, corn and soybeans transpire a huge amount of moisture into the air. Up in Canada, canola fields. Remind me to show you a canola field. Okay, so we're giving off all this radiation. That's all these numbers here and here. And then we have evapotranspiration, which is 22.8%. That's a big number, 78. And what's happening is you take heat from the ground, release it as latent heat, assuming it rains out. And so in order to balance the budget, I need radiation, conduction, and convection in order to balance the budget, which is what we try to do. And that's your energy budget. Do you have any questions on this? Anybody? All right, I'm going to get into another subject. It's still early, but let's go ahead and take, what time is it? 2:20? Come back at 2:25. Let's take a little break. Okay? 2:25. My guess is that we're going to finish up some of this today. And we'll probably finish everything on Thursday. So I'm probably going to set the test sometime between Thursday's class and Tuesday's class. So the test will be this weekend. And then we're going to have plenty of time to do synoptic meteorology, which will be good. So Ryan, Sam, are you there? The test's coming up this week? Okay. Am I sharing the screen now? Okay, so lastly, let's talk about scattering. Okay, so scattering is about redirection of radiation. So I guess I can keep yellow. So basically I have three types of scattering. 1, 2, 3. And everything is based upon this. Alpha, this is Greek letter alpha, is known as a size parameter. And we're going to look at this. Remember, 3 is defined by, so we're defining alpha to be the size of the scatterer scatterer size divided by the wavelength, that which is being scattered. Okay, so remember, this is a comparison. Comparison.
Was it ratio next?
Comparison, ratio,
Fraction.
fraction. So I'm comparing the size of the scatterer, which To determine the size, I'm going to use 2 pi r. What is 2 pi r equal to?
Is that the area of a sphere?
Not area, that's pi r squared.
Oh, circumference.
This is the circumference. Right? So the first case is if alpha is greater than 50. Okay, if that's the case, that means the scatterer's circumference is greater than 50 times bigger than the wavelength. So what that basically means is this: you've got this wavelength coming in and hitting an object that's really big. Do you agree that this is alpha is greater than 50? If the wavelength, because there's the wavelength, is really small compared to this circumference of this big circle. This is known as geometric optics. And what happens is the radiation comes in at some angle. It's such a big object that the radiation bounces off at the same angle. So what we can say is that the angle in equals the angle out. Because the object is so big, it appears to the radiation that it's just hitting a wall. It's hitting a straight line. So we're thinking about wavelengths of light. What in the atmosphere is way bigger than the wavelength in terms of, like, remember, visible light's like half a micrometer. So what in the atmosphere is way bigger than the wavelength?
Water drop.
Oops. Or really what we should think are even cloud droplets, which means any color light hitting the cloud is going to reflect at this angle. And that's why clouds are white, because it doesn't matter what the wavelength is. They all act the same way. They all change direction the same way. Now, sometimes with the light, if it comes in just right, it'll bounce off and then bounce again. And you get a rainbow over here because it's acting like a prism, right? So sometimes light hitting clouds may go through because only so much is reflected. Some of it goes through the water droplet. This is more likely with not a cloud droplet, but a raindrop. So raindrops are so big that the light actually goes through it a lot of times. They don't come in at an angle, they're just going through it and they change direction. They scatter out like a prism. I'm not going to worry about that too much. But understand that geometric optics is cloud drops. And so clouds don't care what color it is. They're all basically white or shades of white, or shades of gray. Now, the second case is if alpha is approximately equal to 1. And what that says is that the scatterer size and the wavelength are about the same. So that would look like this. Do you agree that that wavelength is about that circumference? Okay. Now, is there anything in the atmosphere that's about a half a micrometer in circumference? And the answer is no. But if I were to use radar, which is a longer wavelength, and snowflakes, it does this. Anyway, this is called me scatter. Okay, me scatter. So you need to know this about Mie scattering. It exists, and it's really hard to understand. It's complex. It's a complex process. But there's nothing in the atmosphere that scatters incoming solar radiation, like Mie scattering. Geometric optics, definitely. So other than the fact that you need to know this is a type of scattering, I'm not going to do anything more on it. However, what if it looked like this? What would you say alpha is in a situation like this? What's the value of alpha? What do you say, Ryan?
Well, alpha would be like much smaller, much less than, I don't know what the exact number would be, but it's a lot less than the wavelength.
Well, it's less than what though? Because remember, this is a ratio.
Oh, it would be like a low number, like I don't know, a decimal or something.
Okay, so it's all the numbers are compared to 1, right? If it's equal to 1, the top and the bottom are the same. If the top is small compared to the bottom, then it's less than 1. But you said it's a lot less than 1. And that's what that symbol means. So if I put 2 less than signs, it's a lot less. And this type of scattering is known as Rayleigh scattering. Now, what in the atmosphere is much smaller than a half a micrometer? Because we're thinking visible light is a half a micrometer. What's a lot smaller than that? What do you think?
CCN?
No, CCN are probably more on the big side because they're particulates, right? You can actually see sort of a particulate. What's even smaller than that, though? What's less than a half a micrometer?
Could just be an atom or something.
Right.
Molecule.
An atom or a molecule, right? Those are really small. So Rayleigh scattering is light scatters because of what? Of the air itself. It's the molecules that do that. So that's known as Rayleigh scattering. Now, keep this in mind because I'm going to erase this for now. Any questions on this? Okay. And I'm going to write this equation down. Q in science, not QAnon, but Q in science, is often called an efficiency. So if you see Q in the science, a lot of times you'll say efficiency. S stands for scattering efficiency. How would you define what efficiency is? Basically, simply, real simple. How would you define efficiency, Isaac? Think 2 words.
Well, 2 words that I think of are work. That's work and.
Okay, work definitely has efficiency, but if an engine has efficiency, what 2 words go blank, blank, it works. It's actually a question. Anybody? Right? An engine that's more efficiently works better than one that works less efficiency. So how well does it work? So scattering efficiency is how well does light scatter? Well, light scatters equals to k times the size parameter to the fourth power. When it equals a constant, what we're saying is that this scattering is directly proportional to alpha to the fourth power. What does this equation look like, by the way?
Looks like the stuff in Boltzmann.
Right? E star equals sigma t to the fourth. The irradiance is directly proportional to the absolute temperature to the fourth power. This is how well something scatters is directly proportional to alpha to the fourth. But what is alpha to the fourth actually? Oops. It's actually k times 2 pi r over lambda to the fourth. So how many variables are in this equation? 1, scattering efficiency, how well it scatters, the radius of the scatterer, and the wavelength of that which is being scattered. So this becomes A equals B over C. But do I like equations with 3 variables? What's the first thing I need to do if I have 3 variables in one equation?
Down to 2.
Sam? What'd you say?
You want to get it down to 2 variables.
So what do you do to the third?
Make one constant.
No.
You make it constant. So which one of these 3 makes the most sense to call a constant?
Hey,
You think Q sub S, Aaron?
oh, she said K.
Oh, no. So look, so let me redraw this here for you. Here's the equation.
Oh, I'm sorry.
Right? That's the thing. So how many variables are there? 1, 2, 3. K is already a constant. So the variables are the scattering efficiency, the radius of the scatterer, and the wavelength. So which one of those is best to call constant? What do you think, Ryan?
Maybe, let's see, the Q of S.
What's the big question I'm trying to answer in this section? Why are we talking about scattering?
How well?
No. What's the big overarching principle that brings us into this stuff? What question are we trying to answer? It's in the outline of the class. Do you have the outline from your class syllabus? What does it say?
Are you looking like generally for the class or for this specific part of the class?
For this specific part of the class. In the outline, there's a question with that.
Okay.
You find it, Lena?
No, I'm still looking.
You see that in the outline? The topical outline for the class. It says, why is the sky blue? Well, I just told you that a few minutes ago. Well, why is the sky blue? What's blue light doing?
Scattering.
Scattering. So I'm saying, well, why is the sky blue? What determines the color? The wavelength, right? So blue rather than what? Red? Why isn't the sky red? Why is it blue? Well, blue and red are different because the wavelength varies. But do you agree that it probably has something to do with scattering? So that's scattering efficiency. What's the only thing that doesn't change in the atmosphere? The radius of the molecules. Now, you can say that it kind of does, because what's most of the molecules in the atmosphere? Most of the molecules are what? You know this. Aaron, what's most of the molecules?
Nitrogen and oxygen.
These are about the same size. Right? They're about the same. Then you got argon, which is close. But here's the thing. Does the percentage of these gases change as light goes through the entire atmosphere? Answer, no. So the average size, the average size of the molecules is constant. In the lowest 80 kilometers of the atmosphere. What do you call the lowest 80 kilometers of the atmosphere? This is a stretch. What do you call the lowest 80 kilometers of the atmosphere?
Is that the mixing layer?
Yeah. Lowest,
Troposphere.
the what?
Troposphere.
No, that's the lowest 10 kilometers. That's the lowest 80 kilometers.
Stratosphere.
That's no.
No.
It's an alternative name that we used. I gave it to you in one of the tests. It's the, starts with an H.
Hydrosphere. Wait, no.
It's the homosphere. Remember we said in the lowest 80 kilometers, the distribution of gases is the same. What do you call the layer above the homosphere?
Was it the heterosphere?
The heterosphere. And the heterosphere has the layering of the gases. So when the light's going through the lowest 80 kilometers, 78% of all the molecules it's running into are nitrogen. 21% of the molecules are oxygen. The average way that it scatters is all the same. And it doesn't change. So the best thing to think about is that this is constant. Now watch this, guys. Are you watching? If R is constant, what's 2 pi times R?
Circumference.
Just a constant. What's a constant to the 4th power? Just a constant. What's a constant times another constant?
Constant.
Just a constant. What does this equation eventually become?
Oh, A equals B over C.
What is it? What is this finally? What does this whole equation simplify to? When all those things are constants.
Just
Am I missing anything? Am I missing anything?
lambda to the 4.
right? Because it's lambda, the still to the fourth. So this, and I put K prime, just so that you know it's different than this one, whatever the number is. And again, do I care? No. That becomes the equation that governs Rayleigh scattering. Rayleigh scattering efficiency. So A equals B over C. B is constant. So what is this relationship? Read it to me in English, Zach.
The scattering efficiency is inversely proportional to lambda to the fourth power.
Scattering efficiency is inversely proportional to lambda, the wavelength, to the fourth power. Do you agree that what will shorter wavelengths do?
Make it have a more efficient scattering.
Make that simpler.
A higher scattering efficiency.
Well, when something does something better, it's
More efficient.
Oops. If it's more efficient, isn't it better?
Mhm.
So short wavelengths scatter better than long wavelengths. Do you agree that blue is a shorter wavelength than red? In the classroom notes, did I give you the wavelength of blue? What's the wavelength of blue light in the classroom notes? Do you guys, can you find it in the classroom notes? Here. Did you find it?
0.74 mu.
What did you say?
I said mu. Micrometers, right?
Point what?
0.47
Oh, you're being
micrometers.
dysgraphic. You're switching the numbers. You're not dysgraphic, are you?
This graphic.
You know what a dyslexic is? Sometimes they invert letters.
Oh, sometimes, yeah.
People who invert numbers sometimes read them and they do them backwards. Was that just a mistake, or have you done that before, Zach?
I've done it before, but I've never really thought anything of it.
Does that ever mess you up in class?
I mean, I correct myself after a little bit.
Okay. Well, just so you want, if you're interested, go look up dysgraphia.
Oh.
Dysgraphic. I had a student, and he would do this all the time. He would just read a number out loud and say and reverse the numbers. It is a thing. What's red light?
Visible light?
No, what's the wavelength of red light?
0.64.
Okay, so look over here. If you go, see I'm invisible right now? If I go over here to the question mark, the product description, look what it says. 0.64 micrometers for red light. If I go to blue light, look what it does. 0.47. So do you agree that blue light scatters better than red light? Say yes.
Yeah.
How much better? So answer the question, how much better does blue light scatter than red light? Do it. I'm going to give you, hold on. I'm going to give you a couple minutes to do this. Talk to each other, but I want you to do it. How much better does blue light scatter than red light? Do you know what the answer is?
Aaron says 4.72 times more efficient for blue.
That seems a little bit off. So let's do this, right? So what you should have is this, guys, right? Hold on. Where are you guys? Man, I can't, every time I do this, I lose you guys. Oh my gosh. This is so annoying. Where did you guys go? Well, whatever. I can't see you, but that's okay. So what I'm saying is this, is Q sub S of blue over Q sub S of red. That's the
Are
equation.
you
That's-
writing it down somewhere or something?
We can't see your screen.
Yeah, you know why? Because I didn't share. So where, oh, there you are. Okay. There. Am I sharing my screen now?
Mm-hmm.
Okay. Q sub S of blue over Q sub S of red. That is a fraction, which is a ratio, which is a comparison of how much blue light scatters better than red light. That's what you have to understand about fractions. Guys, I'm telling you for the test, you need to know this. That's how you read a fraction. It's how much more is the top than the bottom. We know that that's going to be equal to K prime, or K, divided by lambda to the fourth of blue, all divided by K prime over lambda to the fourth of red, right? So that's what you should do. Now, what's the first thing you can do? And this is what Zach said. The K's cancel. So now I have 1 over this divided by 1 over that. But 1 over x divided by 1 over y. What's the identity property of multiplication? Have we talked about this before? Any number times 1 equals itself. So what I'm going to do is, what number can I multiply this by? I'll multiply this by y over y. So what's 1 over x times y? Y over x, right? What's 1 over y times y?
Y over Y, which is 1.
Over 1, which means y over x. So when I take a fraction like this, I can flip it like this. So this becomes lambda to the fourth of red all over lambda to the fourth of blue. Now, at this point, there's nothing you could do other than plug in. Although you could do this, right? But you still have to go 0.64 divided by 0.47 to the fourth power. Do you agree? Is this what you did, Aaron? I think you got a wrong number though. So watch this. What I'm going to do is I can get rid of the point. Why? Because this is 64 hundredths divided by 47 hundredths. The hundredths go away. Do you agree that this is almost like 48? 64 over 48, which is 4/3. What's 4 to the fourth power? Do you know what that is?
256.
Good. What's 3 to the fourth power?
81.
Okay, now Now you get your calculator. What's 256 divided by 81?
About 3.16.
3.16?
Yeah.
Okay. Now, do you understand that the answer is going to be, is the actual answer going to be more or less than this? Notice that I made the denominator larger than it should be, which makes the answer smaller than it should be. So so somebody take your calculator, do 64 divided by 47, and then take that to the 4th power.
Hold on. How did you get 64 and 48 again?
We said that lambda of blue was 0.64 micrometers, and lambda of red, no, I'm sorry, was 0.47 micrometers, Sam, and this is 0.64 micrometers. Those are numbers that I gave to you. They're in your notes, but I gave them to you on the satellite page too. So those are just given to you. You got to know those because you need to have that. So if you put the numbers in, you get 3.43. And really what that is, do you agree that's about 3.5? So what was the question I asked you?
How much better does blue light scatter than red light?
And what's the answer? About 3.5 times. In other words, if I ask you, why is the sky blue? The answer is because blue light scatters 3.5 times better than red light. Now, does blue light scatter better than red? Say yes.
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 Does red light scatter some?
Yes.
Does green light scatter some?
Yeah.
Just blue light scatters more. So watch this, guys. When I'm standing on the earth and I'm looking at the sun, well, I'm not looking at the sun because that would be bright. The light is coming in, right? That light is made out of blue light, green light, and red light. And well, there's 7 colors, but those are the 3 primary colors. So some of the blue light starts scattering. It starts going all over the atmosphere until it eventually comes into your eyes from a different direction. And there's a lot of blue light that scatters out. Right? It's going all over the place. Blue light scattering all over. Does green light scatter out? Yes. But not as much. So is there some blue light coming right here? Yes. Goes straight to you. Is there some green light coming this way? Yes. More of it though. And then does red light scatter? Yes. But most of it doesn't scatter out. And so what happens is when I combine, if I mix these colors, if I mix those colors, the amount of blue light that scatters, the amount of green light, and the amount of red light, I get what we call sky blue. So I'm taking sky blue out of white. But what's the opposite color of blue? On the color wheel, remember? We did RGB.
Yellow.
The opposite of blue is yellow. So that makes the sunlight mostly yellow. That's why the sky is blue. Your eyes are more sensitive to the middle of the spectrum. Violet, like, do you agree that violet light scatters more than anything else? Hey, what other kind of light scatters a lot? Do you agree that ultraviolet light scatters? Do you agree that ultraviolet light scatters better than blue light because it's shorter? So on a sunny day, you're in the shade, can you still get suntan? Does anybody know an albino? Have you ever known somebody who's an albino? They're very sensitive to it. They've got to be careful even if they're in the shade, because as long as they're exposed to the sky, they're getting ultraviolet light coming in because it's coming from the sky. Right? So think about this. I'm looking at the sun over here, okay? There's the sun, and there's the sky over there. Do you understand that I'm receiving light coming from that direction? There's nothing there. It's just light coming to me from that direction. And since I can see blue light coming to me, then I should have plenty of ultraviolet radiation, even more coming to me from that sky. So even on a shade, people with albinos have to be very careful. They usually wear a lot of clothing because they can still get sunburn just by being exposed to a portion of the sky. Does that make sense to you? Okay, so what happens at sunset? Here's the Earth, and here you are on the Earth, and here's the atmosphere going around the Earth. Here's the sun when it's straight overhead. Do you understand that the sun is only going through that much atmosphere?
Mhm.
But what happens when the sun is over here? To get to your eyes on the horizon, do you see how much larger of a layer of atmosphere it's going through? Which means you're giving the light more time to scatter. If you give the light more time to scatter, green scatters out, orange scatters out. What's the least efficient scatterer? What's the least efficient scatterer? Red light. So what does the sun look like at the horizon? Doesn't it look red?
Would this kind of, does this have any relation to like um the green?
The green flash?
Yeah.
No. Yeah, maybe. Yeah, Sam, to be honest with you, I haven't thought through enough, but probably. Green is, our eyes are not that sensitive to green. So we're blending in a lot of the colors. But definitely, right, as the sun goes down and the sunset, do you agree it's oranger and redder? Especially true of the moon. Moon straight overhead, it's almost white. But when it's off the horizon, it's really orange. That's because orange and red are the least efficient scatterers, colors scattered. They're the ones that scatter the worst. So now imagine that the sun sets, okay? So imagine that the sun is below the horizon. Are you seeing any direct light from the sun? What colors might go this way the most and still come to your eyes?
Blue and violet.
Blue and violet. And isn't the blue and the violet the last colors of dawn or dusk? Because when you look at the sun in the east, it's orange. But when you look, in sunset, you look to the west. But in the evening to the eastern sky, it's dark violet. Sun sets, the sky is still violet for a while. Until there's less and less light, you can't see it. And now the stars start coming through. You can see through to the stars, and then the sun's behind the earth, and there's so little light that scatters all the way around the planet, we don't see that anymore. But does that make sense as to why you see things the way that you see them? It's kind of fun, isn't this? This is kind of a geeky session, isn't it? where you can see this, but does it answer questions about why this sky looks different? Now, and what color are clouds usually? They're whatever color is hitting them because they scatter according to geometric optics. So all light's hitting them, it's going to be white light. But at sunset, what color are the clouds in the western sky? Orange and red. Because orange and red light are hitting the clouds, and that's what you see reflected. Okay, and if there's a lot of dust in the atmosphere, the whole sky looks red. So and if you're looking to the west where the sky is red, that means it's dusty out there. And if it's dusty, that means it's not doing what? If it's dusty, what's it not doing out there? Lena?
Is it raining?
It's not raining. That's why you see red sky at night, sailor's delight. Because if you see a red sky, you know there's a lot of dust. And if there's a lot of dust in the western horizon, it's not raining. Red sky in the morning, well then now whatever that system is, it's dusty and it's off to your east and you're probably looking to the west. It's not true everywhere and it doesn't really work, but that's where that comes from. Make sense? You didn't know all these things are kind of based on some science. Science. Okay. So in any event, that's scattering. That was the last big section that I want to do today. What we need to do on Thursday is we need to do the general circulation, the global circulation. So what have you done? What do you have left for the outlines, for the worksheets? What chapter are you doing this week? Lena, you're always right on top of it. You and Aaron
Yeah,
always.
this week was 14, and then I think the next one's 8.
What's 8 about?
I have not done that one, but the chapter says it's wind.
It's wind. Okay, so that's really coming up to the next stuff. So chapter 14 should be the end of the stuff for this unit. So on Thursday, we're going to do the general circulation and do some really cool stuff. And that will propel us into the next section. So are you okay taking the test sometime between Friday and Monday? Is everybody okay doing that? I think that should be fine. And what it'll be nice is it'll give us plenty of time to really get this last section, which is my favorite section, winds and physics and stuff like this. I'll be glad to be done with radiation. But something you need to put together is your notes. So make sure you're putting together a really good class set of notes, especially with all those equations. Okay, so if you have any questions, we can talk about it Thursday. Does that make sense to you? I have one more assignment that I'm going to give you right now. And I'm going to let class out 10 minutes early for this assignment, and you have to do this. Go outside. It's a beautiful day. It's going to be nice tomorrow, and then it's not going to be warm again for a couple of weeks. Not like this. So your assignment is to go enjoy some of the weather and go look at the sky and think about radiation and all that other fun stuff. Is that good enough?
Yeah.
All right, that's your assignment. If you guys are watching this on a recording, you still have that assignment, even if it's raining. Go outside. Okay, guys?
Okay.
Have a good one.
Thank you.
We'll see you on Thursday.
All right, see you Thursday.
See you
Bye.
Thursday. Have a good day.
You too. Where is everybody? Well, there you are. Bye, Aaron. Bye, Kevin.
Bye.